Hi everyone, Professor Mankowski here. Now that we know a little bit more about how to compute the variance and how to analyze it, we're going to start using some really cool formulas that use the variance to give us a lot more intel on the data set. And the first thing that we're going to encounter is going to be the Chebychev theorem. And the great thing about Chebychev theorem is it'll work on any data set. It doesn't matter what the data set looks like. It could be bell-shaped, not bell-shaped, skewed to the right, skewed to the left. So how do you use the Chebychev theorem? It's going to work as long as you know two things about the data set. We have to know the data set average and the data set standard deviation. And what the theorem says is that if we take an average of a data set, in this case it's a sample average, and we go 2 standard deviations above the average, 2 standard deviations below the average, we're going to end up with at least 75% of the data in the data set. So what would happen then if we went 3 standard deviations above and below? If we go 3 standard deviations above and below our data set, we would have a bigger range around the average this time, so we would expect that percentage to go up. And it does. We'd get we'd get at least 89% of the data in the data set. So with Chebychev's theorem, how does it work? The Chebychev theorem inventor, he made this new variable and he said, I'm going to call k the number of standard deviations that we travel from the mean. And then he created this proportion, and it's 1 minus 1 over k squared equals a percent. And he figured out that if he plugged k into that equation, whatever the proportion gave you back would equal the minimum percentage of data that you would find going that number of standard deviations from the average. So when we plug in 2 for our k value, our proportion comes back equaling 0.75. And that's how we knew that at least 75% of the data is 2 standard deviations from the mean. So between what 2 numbers then do you actually find that minimum percentage of data? We're going to take our sample average and we're going to add k times the number of standard deviations, or rather, we're going to add k times the standard deviation of the data set to give us the high range. To get the low side of the range, we're going to do exactly the opposite. We're going to take our sample average and we're going to subtract k times the standard deviation of the data set. So let's try it out. Let's use an example. In this question here, it says the average number of calories in a regular size bagel is 240. If the standard deviation is 38 calories, find the range where at least 75% of the data is going to lie. Okay, now keywords for Chebychev is it's always going to list, or rather it's always going to say in a question at least or a minimum percentage. Now, once they gave us at least 75%, we can take our proportion on the upper left and we can start to set it equal to 75%. Once we obtain the value for k, then we're going to plug it into our other 2 remaining formulas to find the minimum and the maximum. So first thing that we're going to do is in our proportion, we're going to change the inequality to an equal sign because it's going to make the mathematics, the algebra, a little bit easier. And the next thing that we're going to do, I recommend taking that 75%, changing it into a fraction. Students try to do all kinds of different things. They try to put in 75 as a whole number or 0.75 and then end up making all kinds of mistakes trying to do the algebra. So the easiest way to get through the maze is to just set it as a fraction, and we'll put in 3/4. Now I want to isolate for k at this point. So we need to get k on the left and everything that's not k on the right. And the first challenge is that 1 is sitting on the equation on the left side. To clear out the 1, we're going to subtract 1 from the left side. And what we do on one side of the equation, we have to do on the other. So we subtract 1 from both sides. And that's going to leave us with negative 1 over k squared equals 1/4. This is better. It's getting closer to only k on the left side. However, we don't want to go around solving for negative k. How do we eliminate the negatives? We're going to multiply both sides by negative 1. And when we do that, we're going to get 1 over k squared equals 1/4. We're going to bring that up onto the right side of the screen here. Now we have 1 over k squared equals 1/4. How do we handle this from here? Cross multiplying would work really well. It's going to let us know that k would be -2 or +2, but we're only going to be using the positive side when we work with Chebychev theorem. So now we know that k equals 2. A quick little suggestion is a lot of students will try to just memorize that at least 75% of the data that would correspond to a k value of 2. So if they see a question saying something about at least 75%, they immediately go and they pencil in k equals 2. While you can do that, you're going to have a different k value each time the percentage changes. And when you do your homework questions and on the exam, it's not always going to be 75%. It could be at least 88%, at least 90%. So you definitely want to know how to work the algebra. Okay, so now that we know k equals 2, we're going to be able to finish off the question. We're going to use our minimum formula. Minimum equals x bar minus ks, plug in the numbers that they gave us from the question. That's going to bring us to 164 for our minimum. Our maximum will be exactly the same, only different. We're going to take that whole formula that we used and instead of a negative, switch to a positive. So when we put in our numbers, we're going to get 316. So now we know that at least 75% of the bagels are going to have between 164 and 316 calories. Okay, let's do another question. And I need to move a item out of my vision on the screen here. Okay, great. So take a minute to read through the question. Okay. So it's saying that the average number of trials it took a sample of mice to learn to traverse or get through a maze was 12, and the standard deviation was 3. And we want to find the minimum percentage of data values that will fall between 4 and 20 trials. Okay, so as we think about this setup, it's a little bit different than the last setup. This time, if we try to work the proportion on the far left, our formula reads 1 minus 1 over k squared is less than equal to a percent. There's no percentage to set things equal to this time. So what that's telling us is we're going to have to work the formulas on the middle and on the right side, find a value for k, and then plug it back into the proportion to get our final answer. Now, we can work either the minimum or the maximum formula to solve for k, and my preference would be to work for positives. So I'm going to go ahead, I'm going to take the high side, and I'm going to begin to solve that for k. So what we're going to do, algebraically, we're going to turn the formula around to solve it for what k equals, and then once we have that, then we'll go ahead and we'll plug our numbers in from the question. So to isolate for k, the first thing that we have to worry about is x bar is in our way when we read this equation from left to right. So how do we remove x bar? We're going to have to subtract it from both sides of the equation. And as we do that, when we have negative x bar plus ks, on the left, we have to match on the right and say maximum number minus x bar. And that's going to clean us up to ks equals the maximum minus x bar. So staying with the left side, ks equals maximum minus x bar. Now we have to get rid of, we have to isolate for k. So to clear out the s, we need to divide both sides by s. And that's going to tell us our k is going to be equal to the maximum minus our average divided by our standard deviation s. So now let's go ahead, let's plug in our values. We're going to solve for k, and it's going to turn out that k equals 2.67. So to finish things off, we're going to take our proportion formula, and now we're going to put in our values for 2.67, and we're going to get 0.86. So what this means is, when we're summarizing everything that we have, at least 86% of the time, it's going to take the mouse between 4 and 20 trials to be able to learn how to get through the maze. Now, the only thing we have to be really careful for in Chebychev is every time we do a Chebychev problem, we have to keep using the word minimum or at least. So that means Chebychev is not that approximate. And the reason why it's not that approximate is because Well, we don't know anything about the data set, do we? The only thing we know is an average and a standard deviation. So if we don't really know anything about the data set, it's going to be very hard to get a much more accurate answer when we do an estimation. And as we know more about the data set, we won't have to keep saying minimum percentage, or at least we'll get much closer towards a concrete estimate. Now, in particular, the empirical rule is the next thing that comes along, where it's going to give us much more analytical power than the Chebychev theorem. Now, what's going to happen is if somebody tells us our data is bell-shaped, then we get to use the empirical rule. And there's two pieces to the empirical rule. First thing it's going to say is within one standard deviation of the mean, you're going to get about 68% of your data. Within two standard deviations of mean, we're going to get much more, almost everyone, 95% of the data in the data set. And if we go 3 standard deviations, then we get almost the full house, nearly everybody. 99% of the data is going to be within 3 standard deviations of the mean. And remember, this only works if you have a bell-shaped data set. Okay, so let's try out the empirical rule then. If we have our examination scores and our average score on the test is a 74 with a standard deviation of 4, we're going to find the 3 different ranges where we're going to get 68% of all our test scores, 95% of all our test scores, and 99% of all our test scores. So take a few minutes, see if you can figure out between what 3 ranges you're going to get all these 3 percentages. Okay, so let's start to think about the solution. For 68% of our data, we can say we're going to use the fact that 68% of the data is within 1 standard deviation of the mean. So if we fill out our numbers we have for average and standard deviation, what we find out is 68% of the students that took that test scored between a 70 and a 78. For 95%, instead of 1 standard deviation, we're going to switch it to 2 standard deviations. And that's going to tell us 95% of the people, 95% of the students that took that test scored between 66 and an 82. Now last, 99% of the students, so almost everybody that took that test, scored between a 62 and an 86. Okay, now that we have our 3 different ranges, we get to part 2 of the empirical rule. So part 2 builds off of the fact that 95% of our data is within 2 standard deviations of the mean. And you might be thinking, well, if I have 95% of my data in that range, that's mostly everybody. So if I have somebody that scores higher than that range or lower than that range, wouldn't that be a really strange circumstance? And you'd be absolutely correct. If we have an observation 2 or more standard deviations from the mean, we refer to it as unusual. So it could be unusually high or unusually low. So if that's what happens for 2 standard deviations, then what happens when you go to 3 standard deviations or more from the mean? We would think that would be even more extreme, and it is. If you're 3 or more standard deviations from the mean, that's when we consider you an outlier. So you're an extremely high score or you're an extremely low score. So let's put it to work. If we have Jane, and Jane takes our examination, Jane scores an 88. We want to know, would Jane be an outlier on the test? To get to the answer kind of quickly, we can use a little something special that we know. We found out before that to be an outlier, you would have to be 3 or more standard deviations from the mean. And the range that we had was between 62 and 86. So that must mean that if we go above 86, that would equate to 3 or more standard deviations from the mean. And being that Jane scored an 88, which is higher than the 86, that means yes, Jane is definitely going to be considered an outlier. Okay, now what if we want to know exactly how many standard deviations Julie was for the mean, and that should say Jane. I'll make that switch real quick. So how do we figure out exactly how many standard deviations she was? What we can do is we can take Jane's score, which was 88, and we can subtract from that the average. Now, once we have the difference between her score and the average, we want to take her distance and get that within standard deviations. So we're going to divide that distance by 4, which was our standard deviation. That's going to tell us that Jane is exactly 3.5 standard deviations from the average. Now, how do we generalize what we just did so we could get it to work for any different test score? We can call Jane's score X. And we can say what we did was we took our X value and we subtracted from it our sample average. And then we divided that by S, which was our standard deviation. And we're going to show how all these different numbers line up to the symbols. And when we find our formula equal to 3.5, our formula is going to be equal to what we call a z-score. And we're going to use z-scores for almost everything between here and the rest of the semester. So whenever you think of z-score, you're going to think of something called standardization. And standardization means you took the distance between an observation and the mean, and you got that distance in terms of standard deviations. And this is a really critical concept in statistics because we measure everything in terms of units of standard deviations. Well, not everything, but very, very commonly we're going to measure in terms of standard deviations, which means you're going to be seeing z-scores all over the place. A good way to think about it is if you make money, you're working a job, how do you measure how much money you're making? And we would say, well, we use dollars. If you're running a race, how do you measure the distance of a race? If you registered, well, most of the races go in distances of K, like I ran a 5K, I ran a 10K. And when we go in statistics, the units that we're going to use for our distances is all in standard deviations. Okay, so now, once we have that, we're going to come back to one other place. We're going to look at our Z formula, and is this formula, do you think, as it is now, written for an average, or rather for a population or for a sample? Which one do you think it is? And our clue is what's circled in red here. Since the X bar is our symbol for sample average and the S is our symbol for sample standard deviation, the formula that we have written here would be standardization for a sample. If we had standardization for a population, the X bar would switch with mu, population average, and in the denominator, the S would switch with the symbol for sigma. Okay, a really great thing about standardization is it gives us this rubber stamp now, because any given data set, we can go along to that data set and we can identify any data value as unusual or as usual or as an outlier. So we have a way of classifying every single observation. So just to recap, we found out that our Z formula is what we call standardization, and it's going to help us find outliers in the data set. Now, if somebody just walks up to you with a pile of data and they say, oh, thank goodness you had MAT150, you know some statistics, can you help me identify outliers in this data set? Can we use the Z formula to help them? The answer is not necessarily. Because remember, the Z formula only works if we know that our data is bell-shaped. So what do you do if the data isn't bell-shaped, or in fact, if you don't know anything at all about the data set? How would you find outliers then? The answer is going to be on the next slide. Hi everyone, Professor Mankowski here. In our last video segment, we were talking about how you could identify outliers in a data set that was bell-shaped. In this video segment, what we're going to do is talk about how you identify outliers if you had a data set, but you had no information on what that data distribution was about. You didn't know if it was bell-shaped, non-bell-shaped, skewed to the right, skewed to the left. And how would you exactly do that? How would you identify the outliers without any intel on the data set? There's a few techniques we have to go through to learn exactly how to do the process. We have to learn about percentiles. That's going to teach us everything we need to know about something called quartiles. Quartiles are going to get us ready for using the interquartile range. And it's ultimately going to be the interquartile range that helps us identify outliers in a data set. So to begin with, we're going to talk about percentiles. And many of you have probably seen a percentile before in one place or another. Really good example of that is if you take a test like an SAT or a PSAT, and they send you a slip of paper in the mail, and they say, you scored in the 85th percentile, or you scored in the 95th percentile. And you're thinking, okay, well, what exactly does that mean? So what we're going to do to illustrate our way into the concept, imagine that Homer Simpson comes in. He takes the first exam with us. And Homer Simpson finds out that he scores an 88%, 88 out of 100 on his test. So Homer's really happy with this. He goes home and he celebrates. And the next day, Homer comes into school and all of a sudden, he's got a big surprise. He finds out that everyone else who took that test scored a 93 or higher on it. So all of a sudden, Homer doesn't feel very good anymore because he's finding out that he actually had the lowest score in the whole class. So if we had only compared his score to the average, we never would have seen the information about how he did compared to everyone else. And that's where percentile is going to help us out. A percentile is going to help us by analyzing what we call relative positioning. Relative positioning refers to how your score compared to everyone else that took the test with you. So if we're talking about an examination and you score in the 85th percentile, that means that you did better than 85% of the people who you tested with. So usually when you take a test, a higher percentile implies that you did better. Although you have to kind of be careful because it does depend on the context clues of what you're talking about. Not always is it going to be true that a high percentile would be the best. A really good example of when a high percentile would be a really bad thing might be if you go to the doctor. And the doctor is going to give you a physical exam. They measure your height, your weight, and perhaps they look at a chart. They look at a chart that tells them, given your age and your height, how much you should weigh. And they tell you that you landed in the 95th percentile for your body weight. Now, if that happened, the doctor's not going to give you a big award and say, congratulations, you have the best body weight. They're probably going to send you to the hospital right away. So we just have to pay attention to what the context of the situation is. So how do we exactly measure percentile then? Let's propose that we have the following scores for test 1 here. And what we want to do is identify the score we have circled 98 and find out what percentile it is. And the only thing that we know right now is we know the percentile is the percentage of people that we did better than. So what do we want to start to probably consider to figure out the percentage of people that we beat? We might probably want to know how many values we had below X, or rather below the score that we're talking about. And since we're talking about 98, we're going to call 98X. We probably need to consider it against the total number of scores that we have. And we're going to call the total number of scores the total number of values. So if we just decided, let's take how many scores we beat, divide that by the total number of values, we'd be almost exactly where we needed to be. The only extra thing that we have to add in is a 0.5 in the numerator, and that's for a correction factor. That's just because we're working with a small data set. And usually a small data set would be less than 100 values. Now, if we take that proportion, we multiply it by 100, that's going to bring us out to a whole number. And it's going to equate to that score being in the 72nd percentile. All right. Now that we know that, let's start to talk about quartiles. If we have a data set that's shown up here, what we want to do is, first thing is we're going to find the mean of the data set, or the median of the data set. Now we have to take into account, do we have an even number of values or an odd number of values in the data set? In this case, we have an even number of values, so our median is going to be the average of the middle two numbers. When we calculate the median out, it's going to be 18.5. Okay, now what we're going to do is we're going to go into that data set and we're going to look in all the numbers above 18.5 and we're going to find the median there. All the numbers above 18.5 is everything from 19 through 22. And again, we have an even number of values, so our median is going to be the average of 20 and 21. That's going to be 20.5. And we'll go ahead, we'll label that median too. Now what we want to do, we want to take another median. We want to consider all the numbers that are less than 18.5 and find the median. So that's going to be everything between 3 and 18. We have an even number of values, again, in that portion of the data set, so we're going to average the middle two numbers, and our median, number 3, is going to be 16.5. It's going to turn out that these medians have very special names. We're going to call median 3, or our third median, quartile 1. The middle median is quartile 2, and the final median is quartile 3. So why do we call them quartiles? It's because they're dividing the data set up into 4 chunks of data. Now what we're going to do is we're going to take quartile 3 and subtract from it quartile 1. That's going to give us a 4. And I'm going to rewrite that over here. And we're going to label the 4 as the interquartile range, or abbreviated more commonly as the IQR. The IQR is measuring the distance across the middle 50% of our data set. Now what we're going to do is we're going to take quartile 3 and add 1.5 times the IQR. That's going to give us 26.5. And in case you're wondering, 1.5 is going to be constant. We're always going to use the value 1.5 in our formula. Now, in our data set, we're going to go and we're going to look and see if we have the value 26.5 up there. If we do have any values greater than 26.5, those are going to be considered outliers for the data set. And in this particular data set, we don't seem to have any, so we are clear of outliers on the high side. Of course, outliers can be on the low side of the data set also. So how do you check for outliers on the low side of the data set? What we're going to do is we're going to take quartile 1 and we're going to subtract 1.5. And that's going to give us 10.5. Okay, so now we go into the data set, we're going to check and see, do we have any values 10.5 or less in our data set? And we do. We find a 3. So we're going to circle the 3, and this is how we'll be able to identify the outlier. Now, once we found an outlier, should we leave it in the data set? Should we take it out of the data set? What should we do with it? And our answer is we're going to investigate. We don't know why the 3 was there. Was it a typo? Was it a number from another data set? So our answer is just going to be, if we identify an outlier, we want to investigate. Now, the next topic that we're going to talk about has to do with standardization. And standardization is very related to the concept of z-scores that we looked at before. So to get an opening example for standardization, if we have a student that's taking a test, our exam right here in statistics, in MAT150, they score an 85. Now, 3,000 miles away in UCLA, somebody else takes a test and they score a 5. And we want to know, did the person from Bergen Community College score higher than the person from UCLA? At first, we might be tempted to just say, yes, they did. 85 is higher than a 5. But there's some problems that get in the way. For example, do we know even what test that person was taking out at UCLA? Was it a statistics test? How many points were it out of? Maybe that test was only out of 3 points. The test that the BCC student took was out of 600 points. So there's so many unknowns, we have a really hard time identifying which score was actually best. And this means we don't really have the scores on a same sliding scale for comparison. So how exactly do you even the stakes then? How do you figure out which score is better? And the answer is standardization is going to help. Standardization is going to take both test scores and get them on the same exact sliding scale for comparison. Now, standardization will work with any data set that you can possibly come up with. There's only 2 things that we need to operate standardization. We need to know the mean of a data set and the standard deviation of the data set, and then we can make standardization work. It's going to be a little bit similar in that it works on the concept of relative positioning, sort of like percentiles did, but it's going to be much more powerful than percentiles. Okay, So what we'll do is we're going to use an example that's actually one very similar to our textbook. However, we're going to do it a little bit differently than it's presented in the textbook. We're going to take a graphical approach to it, or a visual approach to it first, and then we're going to go and we're going to start to quantify how you would use standardization. In our example here, we've got a student. They're taking two different tests, a calculus test and a history test, and we have some information about how they performed on each test, an average for each test and a standard deviation, as well as the scores. And we're going to use standardization to figure out in which case the student scored higher on the test. So first thing I'm going to do, we're going to go ahead and write down calculus and history. And I'm going to make a little number line here. On the number line, I'm going to go and I'm going to write in my average is a 50 on the calculus test. I'm going to go ahead and I'm going to make a range above and below 1 standard deviation from the average. So that's going to be a range of 40 to 60. What we'll do next is we're going to go ahead and we're going to mark the score of 65. And we'll go and we'll write score in there. And we're going to go to the middle of the data set. We're going to start at 50 and we're going to climb up to the 60. How many standard deviations did we just travel to get from the 50 to the 60? That's one standard That's one standard deviation, so we're going to go ahead and write 1. And now we're going to keep continuing the rest of the way to get to the score of 65. That's another half a standard deviation that we traveled. So we'll summarize that off to the right. We're going to say we traveled 1.5 standard deviations. Now we'll do the same thing for the history test. We're going to make a number line. We're going to write the score average of 30. And we're going to go and create a range 1 standard deviation above and 1 standard deviation below the average. That's going to give us a 25 on the low side, a 30 on the high side, and we'll go ahead and we'll write down that that score was 35, so we have that. And just like we did with the calculus test, we're going to go to where the average is, and we're going to walk up to the 35, which is the upper range. How many standard deviations did we travel? We only traveled 1. And since we're right at the score now, we'll just go ahead and we'll summarize. We'll say we traveled 1 standard deviation. So in which case, the top or the bottom, did that person travel more standard deviations from the average? Now the answer is going to be with the calculus, because they are half a standard deviation further away from the average than they did when they took the history test. Now, a lot of students will wonder, okay, do I have to go through a whole graph to get this answer or a number line? Is there a faster way, a formula to get there? The answer is absolutely, there's a formula. The formula is going to be the standardization formula that we had seen before. So what we're going to do is we're going to run the standardization formula for the calculus test and for the history test with our students' scores filled in for the X value, and we're going to confirm the numbers we have on the right for the distances we traveled in standard deviations from the average. So for calculus, if we work out our Z formula, we're going to get to be 1.5. And for our history, our Z formula will give us 1. So we're going to end up confirming the distances that we had marked in green. And on the exam, it's only necessary to run the formula. You don't have to go through the diagramming stage if you don't want to. And I hope this video was helpful.